Hello, today I'm going to talk about the NASA Space Cancer Risk Model version 2020, collaboration with myself and Eladani Kakio at UNLV and Young-hee Kim and Prem Kumar Saganti at Prairie View A&M University. So this model has been evolving for many years. So first, the funding support. So it's from UNLV and Prairie View. And UNLV is in Las Vegas, of course, and Prairie View near Houston, Texas. The model has been developed for about 15 or more years. The first version was just a response to the NCRP reports 126 on uncertainty analysis and 132 on space radiation risk in LEO. This was followed by improvements in 2006 and then some major milestones in 2012 that were reviewed externally by the National Academy of Science, or NASA, and the NCRP. And here we looked at track structure dependent quality factors, different quality factors for solid cancer and leukemia risk, and a never smoker model to represent astronauts. We had some more revisions based on the NASA review. We had objective quality factor parameters that were published in a +1 paper, and then the coupling of the draft and quality factor based on observations of ion truck structure. And then we followed that up with new improved GCR models and non-targeted effect estimates. So the idea of the coupling of the draft and the quality factors, if you look at the particle track structure, this is for an ion particle, you have the core where the doses and ionization rates are so high that it couldn't possibly depend on a dose rate. And then the penumbra, which depends on dose rate at higher doses, but as you go to lower dose and dose rate, it wouldn't. But since the experiments are based on higher doses and dose rates than occur in space, or the limiting asymptote to this low dose rate, you would apply a draft. So we broke up the quality factor into those two terms and using estimates from radiobiology data for the parameters of the model. So the new model has revised low AT coefficients based on the latest data from Hiroshima and Nagasaki, replacing the previous Nscr models. We also made some estimate for radiation worker risk coefficients, but they're kind of noisy and they don't have the same observations as the Hiroshima and Nagasaki. It's kind of complicated by the chronic exposure over many years, different time periods. We also make relative risk models for CNS risks. Novel object recognition has been published last year in LSSR, and then we're looking at a new publication on spatial memory performance, which is showing even a lower risk than the novel object recognition paper. We also have looking at the electron RBE effects on quality factors and the effect of microgravity on inflammation and cancer risk. And as we reported at this meeting, a dynamic leukemia model. So just remind you, non-target effects, if you take a typical dose response here, neoplastic transformation by Bottega et al. With alpha particles, and you take that data and you divide by the x-axis, you get the response per particle or per dose. And you can see as you go below 1 particle per cell, you get this large increase. So a linear response would be a straight line on this curve, and you see this increase below 1. And this is the region in space. We're talking about heavy ion doses for a Mars mission, no more than 5 rads. So most of the experiments are 10 rads or above. So they're largely too high, way too high. So this again leads to the prediction that non-target effects dominate the uncertainty. You can see this is prediction for 1 year in space for 40-year-old females, and they push the risk limits well above what's acceptable. So we believe that should be the prioritization for ground-based research, is to understand non-target effects and get data sets and as many model systems as possible. And to do these studies, you need to do low doses. You need to be doing heavy ion doses from 1 to 5 rads or even lower, and not at 10 rads and certainly not at 1 gray. Okay, thank you. So I hope you read our publications on as these models develop and the publications from the past. Take care.